It's not a particularly a choice, but yeah.
Sorry?
There's not much of a choice.
Well, that's what I was gonna ask.
Yeah.
I would consider not.
Like no one would talk to you over dinner then if you can live stream. No, it's kind of a nice extra thing. Okay. Good.
And then she goes to explain why
Right?
Couple for rather than a class.
That's all right.
He told me to do a class, but then somebody. Maybe everybody.
I don't know that I.
Distinguished. Yeah, is it?
Reading into that, there's one thing I just want to say. I just want to allow him to mirror the screen, otherwise it's annoying for him.
You can find it. Yes, that's maybe nice. The only
The only 2 minutes, a couple, literally a couple.
Yes, no, I think just to get in touch with him actually, because I saw one,
We have
the same
couple of minutes.
before us about. It was.
So it was the recording is working.
And I've read it in the locality
Yeah, it should be all good.
or something like that. And I can't remember this thing, so.
I think if you want to find it, my video panel. Should we? What's it saying? Minimize it. Further carry, would you have some?
No, the lines on the side are actual margins.
I think I think on each click, I'll read numbers and very minor predictions, and find it good.
So you probably,
Big day.
you don't have to click or do it.
That's okay. I can just.
So you use that source. Well, maybe.
Yeah. I
Okay,
see. I just give the select the projection or the slides rather than zoom.
okay. Does this give us the?
I should give you the slide. Yeah.
Okay, I already have it.
Yeah.
Oh, yeah.
Yeah, pick this up from Nick.
Oh, there she is. So I don't know really how to stop that.
I do, but it'll turn on the notifications that more people can't be admitted, which maybe is not.
Oh,
So.
no, we did won't.
Yeah, I'll just admit whoever shows up unless it's an obvious. I don't really know what. Bad actor.
All right.
Donald Trump 47.
Precisely.
Here, Donald Trump 46. Okay. But I'm afraid this may be it for today because out of all seminars and events we're organizing, the numbers seem to go down as we get to the last 2 weeks of the semester. Unless some of you know of anybody who is definitely going to come and who's not here. We don't. All right. Let's start then. Thank you very much all for coming, and it is my great pleasure to introduce John Doherty. John was an undergraduate at the University of Chicago, where he studied physics, history, philosophy, and social studies of science and medicine, I think.
Yeah.
And then moved to the University of California, San Diego to do the PhD, which he did 5 years ago. When he then moved to Munich, to the MCMP at the LMU in Munich, where he has been since then, first as a postdoc and now as an assistant professor for, I think, about the last 2 years or so. John has been publishing in various journals in philosophy of science and foundations of physics. He is interested, as I'm sure you will notice, in particular in questions of the representation, the relation, let's say, generally speaking, between the mathematics we use, in particular in the physical theories, and the world, how they represent, what the relationship is between the mathematical formulations of our best physical theories and the world. They're supposed to be getting at in some important and salient ways. That includes, of course, formal aspect and pretty technical work, but of course it also raises many philosophical, including metaphysical questions about this relationship. And John, as I see it, is interested in very many of these aspects and all sorts of interesting questions that follow from this sort of major theme of interest. Today, one thing I should mention and not forget, I'm very proud to also report that he's also an alum of the Beyond Spacetime project. He was a junior fellow at the University of Illinois Chicago 6 years ago, perhaps.
2017.
Yeah, that's about 6 years ago. So I didn't forget the most important part. Today he will be speaking about gauge theories and homotopic paradigm. Please, John.
Thank you very much, Chris. And thank you for inviting me, Chris and Nick. Thank you all for being here today. As Chris said, I want to talk about gauge theories and the homotopic paradigm. The homotopic paradigm being the name for this view that Gabriel Catrin has been advancing in some recent papers. But in order to orient ourselves, I figured this is beyond space-time. I should say something about quantum gravity, at least at the start. So here's one slide on quantum gravity. So this is also, excuse me. In addition to being, relevant to the topic of the talk, this is autobiographically how I got into this topic. So, when you first learn about, say, geometric dynamics, you're presented with the problem of time. What's the problem of time? It has various features. One formal feature is that you have this Wheeler-DeWitt equation, according to which the Hamiltonian annihilates your state. This is a puzzle because the Hamiltonian also generates the dynamics, and so we have our dynamics is zero. There's no dynamics. There's a Rosen formalism. What's going on here? So I remember when I was first presented with this equation. I think it was in that review article about Kukoc. I thought, well, I think this means it's not dynamical, right? Like there's a zero there, sure, but lots of things are zero. Maybe that's not a problem. But the second sort of thought I had is, well, why do we care so much about this equation? Why should we impose it, right? What's forcing us to do this? And Kukoc alludes to the fact that, well, it's a constraint. It's a Hamiltonian constraint. It appears in a constrained Hamiltonian formalism. And so in order to figure this out, you should go read something about the constrained Hamiltonian formalism. What does the constrained Hamiltonian formalism say? It says, well, the constraints are things that pick out the physical subspace. And so when you hit something with constraint, that should annihilate it. And when it's annihilated, it's in the physical subspace. And I thought, well, what could that mean? What is a physical subspace? I suppose it's something that's subspace you run into when doing physics. That's any subspace because we're doing physics. So what could physical subspace possibly mean? If you read a little bit more about these sorts of theories, you'll find people saying, well, it's the sort of gauge invariant subspace. It's the subspace in which gauge invariance is respected. And we have to respect gauge invariance. And in GR, diffeomorphisms are gauge transformations. And so we must respect them. Okay, why do we have to do this? Right? I feel like, I'm American, I want to decide what I respect. You can't make me respect something, right? And then they say, no, you have to, you don't understand, because look, what are gauge equivalent configurations? They're things that represent the same physical state of affairs. Gauge equivalent configurations represent the same physical state of affairs. This is formally implemented by things like these constraints. So that's why they must be imposed. But this, to me, is philosophically mind-boggling, because what is talk of representation doing in a physical theory, right? Physical theories represent things, of course, but physical theories represent themselves representing something. This seems like just the wrong sort of thing for a physical theory to be talking about. If it's true that this is a physical fact, we should call up the philosophers of language and the philosophers of mind, because we have made major inroads on intentionality and problems of representation. Of course, I don't think this is really going on, but something is going on, right? And so the question is, what exactly? So here are two quotes that I think say in a little bit more detail what the idea behind this represent the same physical state of affairs business is about. First comes from a paper by Gordon Law 2018 called $50 Million Spam Can't Be Wrong. Part of what Law is up to in this paper is trying to point out that philosophers of physics are not paying sufficient attention to an important distinction between kinds of transformations that appear in physical theories. He termed the distinction between gauge and physical symmetries. So he says, gauge symmetries are symmetries that relate solutions that cannot be taken to represent distinct situations, whereas physical symmetries are symmetries that relate solutions that can be taken to represent distinct situations. So again, I sort of rankle at these commands. Who says that I can't do it? In fact, watch me. Here's the sun, here's the moon. I'm now representing the solar system. Do it with these two things instead. You can represent whatever you want with whatever you want. That's how representation works. There must be something else going on. But what could it be? Right, that's the question. Quote number 2 is from Richard Healy's book, Gauging What's Real, where this is his preliminary characterization of what a gauge theory is. He says, the gauge theory addresses its subject matter via representation with redundant elements. In its standard formulation, there are more variables than the independent physical magnitudes whose behavior it seeks to describe. So this redundancy talk is very common in these sorts of theories, and I think it's pretty puzzling for the reasons that I've been saying. If the theory is saying that it has redundant features, then the theory is both representing these things as distinct and as the same. That's a contradiction. Hopefully our theories are not engaged in this kind of nonsense. So this is, to me, the puzzle about gauge theories. What is the content of a a theory is classifying some transformation as gauge or as not? It's common to say as physical, as Balaka's, so I'll do the same. What's the difference between a gauge transformation and a physical transformation? What could this mean in a way that doesn't presuppose substantive claims about representation or realism? I won't say much about the realism stuff, but if you want to, we can talk about it in the Q&A. What could the content of gauge classification be? More specifically, here are two things that I can answer to this question it ought to answer. First, why can't we take gauge-related solutions to be distinct? What does this can't mean? Obviously, I can do what I like, so this is some deontic command. What's the ground for it? Second, how can a theory be redundant by its own lights? What could redundancy mean in these contexts? And then, hopefully answering these questions will give us some sort of philosophical consequences, given that either these are, some of our most fundamental and important theories, and so they tell us something about the world, or we're interested in sort of mathematical representation in science more generally, and there's something funny going on with representation here. So in a couple of recent papers, in the bibliography, Gabriel Catran has given some answers to these questions. And his observation, broadly speaking, has 3 parts. First, he says homotopy theory, this particular area of mathematics, supplies apps tools for interpreting gauge theories. And he says, on the basis of this, there's 2 philosophical conclusions that we should draw. First, we should reject the principle of the identity of indiscernibles. Second, we should adopt a particular flavor of constructivism about logic. So I'll say more about all 3 of these things, what the homotopy theory is, PII, and constructivism. I just wanted to set out, here are the 3 parts of this view. I don't want to say much about this. I just want to say what it is and grant it. And then I want to complain about these 2 features. So that's what I'll do. First, I want to just grant the homotopy paradigm and tell you what that means. Then I want to talk about this argument he has that we should reject the PII. And I want to say that I don't buy this argument, sort of for 2 reasons. First, I think the reasons that he gives for rejecting the PII are incompatible with the motivation for the homotopy paradigm in the first place. And so there's a kind of undercutting going on here. Second, even if we do adopt the PII, I think it just doesn't address the puzzle of gauge. And so we shouldn't do this, and even if we do, it doesn't matter. Second, I want to talk about the constructivism about logic business. And I want to say roughly the same thing. First, this can't have any direct impact, having some views about logic or mathematics. Because there's some story you need to tell about how the logic and mathematics are related to the physical world. And once you tell that story, that'll give us a story about how it indirectly impacts it. That's going to undermine the argument for destructivism, say I. So that's what I'll do in the next 3 parts of this talk. So let's start out with the homotopic paradigm. First, just to dazzle you with some of the features, right? So observation in quantum field theory, cohomology groups are everywhere. What's a cohomology group? Doesn't really matter. They're things that have an H and a number in front of them. For example, gauge equivalence classes of flat EM potentials on a trivial bundle are labeled by the first cohomology class of the underlying interval M. The magnetic flux of a U1 Yang-Mills theory lives in the second integral cohomology group of M. Vacua and n-dimensional G-value Yang-Mills theory are labeled by the fourth integral cohomology class. Gauge equivalent actions are related by the 0-3 RST cohomology. There's a whole bunch more. It's not so important what these are. What's important is that this is a recurring sort of pattern where the same kind of object shows up a whole bunch. And even that might not be important. What might be, so the first question sort of is this important, right? So one dispute that you might have as a philosopher of physics is to say, sure, this math stuff shows up a bunch, math shows up everywhere in physics, who cares, right? One way that we sort of frame this dispute is to say, well, what's the physical significance of it, right? So for example, take the second option that the vacua are labeled by this fourth integral cohomology class. Here's a kind of dispute you might have, is this significant or not? Here's an example of people who have had this dispute. Richard Healy, in his 2007 book and elsewhere, has argued that, in fact, vacua are not labeled by this. In fact, there's a unique vacuum. And then this has a bunch of theoretical payoffs, right? So he's got this argument that physically we should think there's only just one vacuum. They're not labeled by these. This is a mathematical quantity some people can define in some representations of gauge theories, but ultimately we shouldn't think that it's physically interesting. I replied to him and said, no, we should think there's more than one vacuum here, even if you adopt Healy's theoretical commitments. So everybody knows, or everybody who knows that like this is the answer you get if you plug into, say, textbook QFT, or if you want to get fancy with the fiber bundles or something like this. Healy says, yeah, that's what you get if you use this fancy stuff, but you shouldn't. You should use my theory instead. My argument is then, well, forget about the fancy stuff too. Look at the empirical results. I think, Healy, you should agree that we need to have these multiple vacua. So this is one kind of argument we might have. It's not the kind of argument I want to engage in. I'm putting it up as a kind of contrast. A slightly more interesting kind of argument you might have is, okay, well, granted that these things are all physically interesting, what should we say about that, right? What's systematic can we say about this? And there's various answers to this available in this literature on the philosophical interpretation of gauge theories. So sort of a random, but hopefully representative selection. So Ehrman has this paper in that 2003 Brady and Castellani volume about, I think it's called An Ode to the Constrained Hamiltonian Formalism. And it's all about how philosophers should think constrained Hamiltonian formalisms are the paradigmatic gauge theories. Theories that admit this formalism are paradigmatic gauge, the paradigmatic gauge theories. So if we want to understand gauge theories, this is the formalism we should study. And other formalisms sort of are relevant insofar as they reproduce the constrained Hamiltonian fiction. Leeds in the 99 paper argues that, well, it's connections on principal bundles that are really what we should care about. Healy in 2007, that's a book-long defense of the idea that what we should care about are holonomy maps. For the purposes of this talk, it's not so important what any of these are. They're different sort of mathematical theories or frameworks or clusters of ideas, concepts, methods, proofs, propositions that are different ways of trying to systematize the individual mathematical physical facts. In this 2022 paper, Catren says, there's another way of looking at all this that people have been kind of in the background developing, mainly physicists, to some degree philosophers. They've been saying, look, here's another area of mathematics that maybe we should be looking at, namely homotopy theory. And homotopy theory has various results and tools, paradigm examples, et cetera, that are going to model gauge theoretic type stuff really well. So this is a claim about, it's a really general sort of systematic claim, and I don't want to interrogate it because I want to just grant it, which is maybe not surprising because I'm one of the people that doing this. But here's an example to give you an idea of the flavor of what is going on here. Sorry. Let me say a little bit more about what the claim is about homotopy theory here. So to give you some slogans to sort of pick out the theory itself, here's from the introduction of Emily Reel's categorical homotopy book. The central project of homotopy theory, she says, broadly defined, is to study the objects of a category up to a specified notion of weak equivalence. These weak equivalences are morphisms that satisfy a certain closure property vis-a-vis composition and cancellation. That's also satisfied by the isomorphisms in any category. But weak equivalences are not generally invertible. So homotopy theory is interested in weak equivalence. Weak equivalence is like isomorphism, but a little bit generalized. Another slogan, this time from a note by Clark Warwick. I think of homotopy theory as an enrichment of the notion that equality, dedicated to the primacy of structure over properties. So this is, I think, a relatively common, though perhaps controversial, characterization of what homotopy theory is up to. Let me give you a brief illustration of the kinds of examples, questions, methods of homotopy theory. This is the next only slide with the equations. I apologize for doing the mathy stuff. But sort of as an illustration, think of the two following maps. One of them is the map from the circle to the real line that just projects out the x coordinate. So here's a circle, here's the real line. This is the map that just sends this point to this point, and this point to this point, and this point to the same one. So if I pick out a particular point on the real line, say here, I can ask, what's the fiber over this map? That is, what are the points of the circle mapped to this point? Well, there's one here and there's one here. If I choose it over here, well, there's none of them. If I choose it very carefully, so it's right at x equals 1, then there's exactly 1 point. And so this map F that just projects down the coordinate has a different fiber or pre-image at this point, depending on which point you're looking at. But now compare this with the map from the circle to the point that just sends everything to that point. These are different maps, they have different codomains. They obviously, I think, once you sit down and work through it, have different sort of fibers and as pre-images, right? The pre-image of this point is the whole circle. And so these are just the sort of fibers of these maps, very different, not equivalent in any real sense. Unfortunately, for the homotopy theorists, the map from the real line to the point is a homotopy equivalence, and so as far as the homotopy theorist is concerned, these are the things that we need to treat as equivalent. Of course, it can't be isomorphism here because there's only 1 point here and there's really many there. So this is an illustration of the sort of more general kind of weak equivalence that we're talking about. So what we need, or what the homotopy theorist needs, is some sort of theory that will ensure that you treat these two cases the same way. Because if you treat them in this sort of naive way, you get different answers. And this is violating the kind of equivalence we're interested in. Here's the solution. We've got a machine called the homotopy fiber. You turn the crank and it gives you the right answer. So in general, the homotopy fiber of some map H over some point y of y is roughly the space of pairs x gamma, where gamma is a path in y that begins at the image of x, the first entry, and ends at y. And if you sit down and you work through the calculations, you'll find that the homotopy fibers of these two maps are both the same in the sense that the homotopy theorist is interested in. And so this construction does respect the kind of equivalence between these two maps that we're after. Okay, what should we, so I've given you this example now. It's supposed to illustrate some feature of homotopy theory. I'll give you another instance of this example in a second. But there's, I think, a kind of natural reaction that people have when they're first presented with this set of ideas, which is, okay, you've drawn some sort of topological spaces and given me some weird counterexamples, but like, what does point set topology have to do with anything? Why are we talking about point set topology when what we really care about, all of us here, is physics? And physics is more than just topological spaces. Well, examples are examples. What we really care about is what we might call abstract homotopy theory. And this is really the perspective that Cottrell is after, that he identifies, I think correctly, as arising in mathematics in the past 20 years or so. More than 20. Parallel development since Noether, maybe. And according to this sort of perspective, homotopy groups, these sorts of H things, are coarse-grained invariants. And the thing that they're really capturing are higher categories. And so when you look at sort of the zeroth homotopy group, well, that's the isomorphism classes of objects. When you look at the first level, those are equivalence classes of isomorphisms. Then there are equivalence classes of isomorphisms of isomorphisms. And so what we really care about higher categories, we get these coarse-grained invariants. Coarse-grained because we're taking these isomorphism classes and identifying, crunching down these things that are merely isomorphic in our usual set theoretic representation. And then abstract homotopy theory is the study of these higher structures rather than being a part of topology. It has its history in topology. This is where we first encountered many of these structures. But abstract homotopy theory, the kind of thing that Tren is after, is really an issue of these higher algebraic structures rather than topological spaces themselves. Okay, so that's very briefly what homotopy theory is vibes-wise. Here's what has anything to do with gauge theories. Question: what is an asymptotically trivial electromagnetic configuration in the sort of situation where we're thinking about potentials? So if we're in QFT or the sort of preparing ourselves for QFT, we think, well, the electromagnetic field is given by a gauge potential. This gauge potential has a certain curvature. That's the electromagnetic field in the classical theory. But certain gauge-related fields, these we want to treat as somehow the same, somehow not. This is the big puzzling thing what you say about this from the first slide. Well, if I ask you, what's the configuration that is sort of trivial out at infinity? I think the first thing you might say is, well, it's the configuration such that when you look at infinity, it's zero or trivial. Or if you want to be fancy about it, it's the fiber of this restriction map from configurations of over spacetime to asymptotic configurations over zero, the trivial configuration. Or, in yet other words, it's a configuration A such that take the limit of A as it goes out to infinity, you get zero. What if instead we take the homotopical sort of version of this? Then what is it? Well, it's the homotopy fiber of the same map. And if you unwind the definitions, what you find is this ends up being a pair of a configuration on your spacetime, along with a particular gauge transformation from that pair to, or from that configuration to zero at infinity. So you might write this as A goes to a pure gauge at infinity, though one needs to remember here that really G is only defined at infinity. So you have to be careful with treating infinity in these cases, but that's not as important for us. What's important for us is that this second option correctly counts the vacua. Why is it correct? Well, that's what I argued in my paper against Healy. This is what I had in mind in that paper and alluded to as a footnote, in fact, that this is really the way that we ought to count vacuum instead of this. And so the homotopy fiber gives us the right answer. The ordinary fiber gives us the wrong answer. This is what I want to just grant Tren, that yes, the homotopy theory, that's right. The interesting question that I want to now engage with his is, so what? Assuming that homotopy theory gets it right, what should we think? Here's examples of answers to that question for other formalisms. If the constrained Hamiltonian formalism really does get at what is essential about gauge theories, then, as Erman argues in that 2003 paper, indeterminism or funky kinds of determinism are really what gauge theories are all about. If you think that bundles really represent what's at root interesting about gauge theories, then really gauge theories involve these relational properties, and that explains all of their features. Healy's 2007 is sort of a book-long argument that holism is the significance of gauge theories because of this holonomy representation that he favors. So what kind of answer could we give to this question if we like this, if we adopt this sort of homotopy perspective? These are the answers that Tren gives. First, the homotopy paradigm engages in two important ideas, namely, first, a rejection of Leibniz's principle of the identity of indiscernibles. Second, a constructivist understanding of propositions as types of proofs. So far, I've said stuff that Tren thinks and I want to agree with. Now I want to say these are two things he thinks that I think are wrong. Thing the first, identity of indiscernibles. Tren has two subclaims here. First, he says mathematics cannot get rid of indiscernible entities. Second, the homotopic paradigm is the furthest development up to now of this emancipation of mathematics from the grips of the PII, as he puts it. He doesn't like the PII. I myself am sort of neutral on it, but for the purpose of this talk, I'm going to say it's good. What's his argument against the PII? Well, he says, look, there's no real defensible version of it. So what does the PII say? Well, it says if there's for all properties P, A and B satisfy that property in exactly the same cases, then A is equal to B. Now this is schematic. Why? Because I haven't told you what P is supposed to be varying over. If you let range over all properties, then consider the property being equal to A. Then if A is equal to A in just those cases that B is equal to A, well then B is equal to A because of course A is equal to itself, therefore A equals B. But complaint, this is trivial, right? If we included the property as being equal to A, then the PII is vacuous. I mean, it's not vacuous, it's true, but it's only a little bit more than vacuous. And so what we want, if we want something metaphysically rich, is we want to restrict the domain of this quantifier so that we can get a stronger kind of claim. Now, perhaps the most obvious restriction here is to say, well, include only qualitative monadic properties. That's the kind of thing that oftentimes metaphysical debates about the PII amount to. They're thinking about, well, what if we don't allow for sort of like properties like being itself or whatever, being A? That refers to a particular object, and so it's not appropriately qualitative. And we're not interested in sort of relational, etc. Well, says Katran, then what if we weaken it? Do this sort of grades of discernibility stuff from Quine. Well, says Katran, if you allow qualitative relations, then there's counterexamples. If you allow sort of for weak discernibility type relations, there's further counterexamples, etc., etc. And so he thinks, look, there's all these people trying to save this principle, but they should just give it up. And really, I think there's one argument he returns to a number of times, which I consider to sort of be the master argument here, which looks like the following. Call it the Burgess, Karen, and Bushwick argument. Mathematics and mathematical physics are full of homogeneous structure. So to take this example from Bushwick 2009, consider a homogeneous structure like an FOW cosmology. What is an FOW cosmology? Well, it's a homogeneous and isotropic spatially cosmology. It's got just this handful of parameters. We use it to do a cosmological standard model. Because it's spatially homogeneous and isotropic, every point is perfectly similar to every other on any given spatial slice. But obviously these points are numerically distinct because there's more than one space-time point at a time. So the PII stands refuted. So this is a summary. Obviously, Bushwick is extremely careful to go through all of these premises. I'm not simply because Katran wants to grant this, and I want to grant the success of this argument anyway. This is supposed to be an instance of this much more general idea that homogeneous types of structures are unavoidable. Whenever you have homogeneity, you have a violation of PII. So you should give up the PII. Now, really, and maybe this is another thing I should have emphasized on the slide. Bushwick, along with Burgess and Karen, are arguing against structuralisms. Them in the case of mathematical structuralism, Bushwick in the case of space-time structuralism. And so really, they're interested in the PII insofar as the structuralist seems to want to define identity in terms of structural identity or sharing the same sort of structure. And this is the place where I think Katran slides into talking about structure instead of the PII really. But supposing that we grant this sort of success of this argument, Katran then says, look, we should just give up on the PII. We've got these arguments against them. They all have this sort of form. They're all good. We should just stop trying to save it because there's no reason. What we should do instead is reject it. And then in doing so, recognize that mathematics has moved forward by accepting the existence of indiscernibles at face value and by constructing new mathematical tools capable of formalizing the very structure of these indiscernibilities. And so thought is, well, let's take age equivalent configurations to be numerically distinct but indistinguishable. So this is the sort of first lesson that Katran wants to draw from the success of homotopy theoretic methods in thinking about gauge theories. That homotopy involves numerically distinct but indistinguishable objects. We should think of gauge theories as involving the same. So there's sort of two things I want to say about this. First, we somehow now started talking about, in the sort of master argument now, really we've somehow slid into talking about structuralism instead of talking about the PII. And structuralism carries with it particular baggage, right? So even if you think Bushwick is successful, as I do, You might think, well, we never should have believed in that kind of structuralism in the first place. Unfortunately, many people did, and now they should know better. But that's just because we had a bad theory of structure. And with it, we already had a theory by which we could formalize the structure of the indiscernibilities that come with that theory of structure. It's from Frege. Frege gave us a theory of quantification, a logic of quantification in the Begriffsschrift that has three interesting features for our purposes. First, we represent generalities as quantifiers. Second, we are now able to talk about relations in a way that categorical logic could not. And third, we distinguish constants and variables. These are three features of Fregean logic that were not features of its predecessors. These, of course, work together because who cares about the difference between constants and variables? Well, I care because I combine them differently with quantifiers, these sorts of things. And so, you know, there's really is a kind of, there's new expressive capacity that we had got with the introduction of Begriffsschrift that we didn't have before. And Frege puts this to use in the Grundlagen, or tries to in his definition of numbers. In this section 65 and a couple sections before, he realizes that, well, look, because I have this new logic, I can now talk about relations instead of thinking of relations as sort of things that are not totally exactly expressible within my sort of two-term logic. I can just say the relation blah, such that blah, 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 using my new sorts of concept script. And because I can stipulate identity relations, what I can try to do is define numbers by defining equinumerous, defining the relation of having the same number as. And so this is going to be his strategy. But he has a series of worries in the mid-60s, section 60s of the Grundlagen. One of which in section 65 is like, well, hold on. The laws of identity involve various things. It's symmetric and reflexive and transitive. And he says, if you have holds of it. And if I just try to stipulate identity, who's to say that it's going to actually fit these laws of identity, right? I could have gone wrong. I can introduce a contradiction in my system when I try to stipulate laws of identity. Well, luckily, we are now able to talk about relations, and we're now able to say that relations have certain second-order properties like reflexivity, transitivity, symmetry, which we can use both in the Begriffsschrift to show that arithmetic is analytic a priori, and in the Grundlagen to define numbers. Well, of course, there's a sort of placeholder in 68 when he defines it, and then he fills that in section 10 of the Grundgesetz, and then Russell shows him how this works. But the general point still holds, I think, which is that we are able to talk about relations, and because of this, we can stipulate identities, and moreover, we have a theory of when identities are able to be stipulated, namely when it's an equivalence relation. And so, homotopy theory is not giving us a new theory that we've seen yet about stipulation of formalizing of equivalences. We got it. It's equivalence relations. It's something which now I think we think of as relatively trivial. But even if this is really supposed to be some kind of lesson that we're learning, I think it doesn't help us when it comes to gauge theories, because the question of Paul was, why can't we treat gauge transformations as symmetries? And trying to answer to this, well, we can and we should. So I don't really have time or space to get into like, well, why is he wrong about this? I just want to gesture at the things I started with, where everybody kind of agrees there's this distinction. Physicists in particular think it's really important. And so we need to have something to say about it. And Trent says, well, there isn't one. Gauge is just a particular kind of symmetry. Symmetry that's very, very exact, I guess. And moreover, I think it doesn't really hook up with the homotopy theory at all, because if the homotopy theory is supposed to be giving us a homotopy fiber instead of an ordinary fiber, then we've got no real explanation here. Why should we care about particular choices of equivalences that witness a particular kind of equivalence relation? I just don't think there's anything to say. Problem number 3, which I'll only allude to, not say anything more about, is that I think, in this 2023 paper, Trent goes into some detail engaging with the sort of Fregean account of abstraction. And I think that it also doesn't work particularly well on grounds of, these issues of language and concepts, but that's getting too far afield for this talk. So what I want to do instead is to just move on and say, here are my complaints. So Observation, the homotopy paradigm conflicts with the sort of broadly forgiven conception of structure and qualitative similarity. This is what Burgess and Karen and Bushwick have taught us. Dutran says, well, in the face of this, we should stick to the Phrygian account of structure, but we should now treat gauge equivalences as a particular equivalence relation because we should just sort of think qualitative similarity is the more interesting thing, but we should just accept that there's this numerical, things are numerically distinct, and there's all these numerical distinctions everywhere. We just need to somehow care less about them or something. And my reply to this is that, well, this doesn't really address the puzzle of gauge theories, and in fact, it makes it worse because now it's even harder to see. We have to somehow play around with the numerical identity and qualitative identity and whatever this sort of gauge physical distinction was before. So I think there's a specific way in which it makes it worse, but I wanted to avoid some of the mathematical details. Okay, so that was sort of plank one. Dutran says we should give out the PII. I think, yeah, do it if you want, but that isn't related to gauge theories. Second, constructive logic, or as he put it before, propositions as types. So what were the two important ideas? First, rejection of the PII. Second, constructivist understanding of propositions as types of proofs. So really briefly, what could this be about? So there's a certain sort of interpretation of logic that one encounters when one studies constructive logic called the Brouwer-Hagen-Grove interpretation. And it's something that applies to type theories. So a type theory is a particular kind of formal system. It belongs in the same box as categorical logic in the Aristotelian sense, quantificational logic in the Phrygian sense. Right? These are various formal systems in which one can try to articulate distinctions and articulate logical relations between different kinds of claims. So most of us have studied only untyped logics, right? If you've ever done, just first order logic or add some modalities, these sorts of things. And all of these, we're interested in judgments of the form phi or some sentence phi. And we want to be able to characterize the consequence relation, which relates some set of sentences to some other sentence. And we want to characterize validity in terms of the form, where form is given by sort of theory of logic that goes in here. A type theory, by contrast, derives judgments of the form P is of type P. This is much easier when it's written because you can't speak in capitals. I always forget this. I'm sorry. But so with the type theory, what you're doing is you're saying that little p is a term of type big P. That's the kind of thing that we can judge true. And what we want to derive are consequence relations between judgments of this form and judgments of this form. And so when you're just presented with untyped logic and typed logics, there's kind of a puzzle. How are they supposed to relate? I said before they're supposed to be in the same box as each other. They're both formal systems, but at least on the surface, their basic notions have nothing to do with each other. And so it's hard, we all know how to translate natural language into untyped first order logic. We don't know how to do it with type theories. Even though, of course, this is in part what they're designed to do. So the BHK interpretation is a general way of relating these two kinds of formal systems. It says that showing that a proposition phi is true corresponds to giving a term of a corresponding type. So for any proposition phi, there's some corresponding type capital P. Showing that this proposition is true in an untyped logic is the same kind of thing as exhibiting a term of that type in the typed logic. And vice versa, giving a term of type P corresponds to giving a proof to the corresponding proposition phi. So this is sort of a general picture about how to relate these two different kinds of formal systems. They're supposed to be able to do the same kinds of things. Any sentence has a corresponding type and vice versa. Moreover, I didn't write this, but conjunction among sentences corresponds to Cartesian products of two types. Disjunction corresponds to disjoint product. Implication corresponds to containment, right? There's kind of systematic relationships between the logical quantifier connectors on one side and the type formers on the other. Natural question, to what do identity statements correspond in the type theory? Answer, Martin Lowe 75, well, they're a particular kind of type, obviously, because everything's a type. What kind of type are they? Well, under the BHK interpretation, they correspond to propositions in this form. And so to prove that that is true, what we need to do is exhibit a term of that type. So why not just say, a term of this type is a proof that A equals B. This is what Dutran wants to say. Two observations are relevant for us. First, Hoffman and Stryker showed in '98 that there exist models of modern Lowe type theory in which this type has distinct terms. And so there must be two different ways to prove that A equals B somehow. And then more generally, Audi and Warren in 2009 and Volodski about the same time independently showed that identity types in normal type theory can be given a homotopical interpretation, where a term of type A equals B is an isomorphism in some sort of higher category. And then a term, if you give me two terms of this type, I can form the identity type of those, and that's going to become two isomorphism, so on to infinity. This is going to be the connection to the homotopy stuff I've been talking about. And this is what Katrin says. So he says, look, we should think of identities as being terms of a type. And we should think of terms of a type as being proofs of the truth of the proposition corresponding to that type. Why should we think that? Well, because he says first the BHK interpretation captures a certain concrete practical dimension in mathematics. When you're doing a proof, you're proving something. At the end, you sort of say, okay, I'm done. I'm not going to look at this again. I know that thing's true. All I care about is the truth of the proposition. Katrin thinks this is a sort of distorted way of looking at mathematical practice. Second, he claims when you think about how you actually prove identities, think about how you do it in geometry, say. He says they naturally correspond to transformations between qualitatively indistinguishable numerically distinct objects. So when you show that two triangles are congruent, what do? Well, you look at the two triangles and you sort of move one onto the other. I guess you should really do that instead. But and so there is a natural correspondence between, he says, terms of a type, because these terms of a type are proofs, because these proofs are connected to transformations or qualitatively indistinguishable numerically distinct objects, these things all mesh together very well. And so proposal, this is what we should say instead of PII, we should adopt the principle of equality types of indiscernibles. Rather than mistaking indiscernibility for numerical identity, expand and typify the notion of equality to encompass numerically different indiscernibles related by concrete equivalences. So this is an argument for roughly why we should adopt the BHK interpretation. What does this have to do with physics? How do we hook it up? Here's the kind of argument he gives. As far as I can tell, it's an argument from cases, right? If you adopt this kind of picture of logic, what is the homotopy fiber? It's just the fiber said homotopically. So in the case of, say, this asymptotically trivial sector we talked about before, and this says that an asymptotically trivial configuration is a pair A, G of configuration A and an equality G between the restriction of A to infinity and 0. And so when you sort of speak typically, or typically, or type theoretically, just say the thing that you mean, or say the thing that you thought with the fiber, but interpret it homotopically, you end up with the homotopy fiber, everything works out very nicely. So I think this is supposed to be the justification for thinking that somehow there's something illuminating about the BHK type theoretic interpretation of gauge theories that it sort of gets these cases consistently right. There's more examples I can give if you like. I just want to stick with this running example I've been using. And so the whole picture that Katrin offers after adopting these two sort of claims is that there's really two generalizations that he wants to make when it comes to how we talk about identity. First, we should admit the difference between numerical and qualitative identity and sort of care more about qualitative identity in a way that I'm not totally able to articulate or grasp, I suppose. Second, we should admit the distinction between propositional and typal identity. Right, the kind of identity proposition that it's either true or it's false in the story, and the sort of type theoretic idea thing where there could be a whole bunch of terms of the same type, and these terms can correspond to different sorts of things. And these are really, I think, and he says, different kinds of generalizations. But the goal is to get to talking about qualitative typal identity in the case of gauge theories. I've already said why I don't think talking about qualitative identity doesn't get us anywhere with gauge theories. Let me say why I don't think talking about the BHK does either. I think that there's a relevance objection. I think that it's not clear that talking about the BHK interpretation helps at all with the interpretation of gauge theories for the following reason. The BHK interpretation gives a propositional interpretation of type theory. It says if you understand propositional logic, or first order logic, or any of these things, then you can understand type theory by translating it using this correspondence. But I think nothing about physics follows or could from this correspondence, because this is a claim about how two formal systems relate to each other. Neither of those formal systems is a formal system about physics. So nothing could issue from this, I think. I don't see how it possibly could. What does issue from this is if you adopt the BHK interpretation, it gives you a certain picture of how the type theory could be. If you then adopt that picture of how the type theory could be, then it sort of opens up this conceptual space of certain theories having non-trivial identities, which is also what the homotopy theorists were after anyway. And it'll turn out some theories have these non-trivial identities and some don't. And so if we want to know of any given theory, whether it has it or not, you need to go look at the theory. You need to, I think, go do some experiments. So sure, maybe we can go figure out whether some particular theory is well modeled by this sort of typal identity. But like talking about that means I need some story about mathematical representations, perhaps a very sketchy one, but still some kind of story. And then that story is going to give you a second model of typal identities that's distinct from BHK because it's a model of typal identities in physics or in mathematical physics, as opposed to in terms of other kinds of logical systems. And so I think, sure, this seems pretty attractive. Think about type theory as giving us some kind of handle on the formal structure of these gauge theories. It does seem to match pretty well. I'm willing to grant that. But I don't think that BHK is illuminating at all. I don't see any reason to think that it's attributing something to this interpretation, which I think is good because I don't like, as I've alluded to, I don't want sort of philosophical claims about logic or mathematics to have any direct sort of physical kinds of consequences. Okay, so let me wrap up. The question of the talk was something like this: granting the success of abstract homotopy theory as an organizing principle for understanding gauge theories, what's the philosophical significance of this? Katren says, well, there's two things that we should learn from this perspective. First, the PII is false. Second, we should be constructivist about logic, and in particular adopt this BHK types of proofs perspective. So against this, I argued that, well, the arguments against PI presuppose sort of anti-homotopic conception of mathematical structure, one given by these sorts of equivalence relations rather than homotopies, such that, for example, it would still recommend the ordinary fiber instead of the homotopy fiber, or maybe the ordinary fiber of the quotient, something like this. And anyway, rejecting the PI doesn't address the main puzzle, which is what does it mean to say that we can't take gauge equivalent configurations to be distinct? He says, well, we can and should take them to be distinct. As for the propositions as types claim, I mean, I think that the argument by cases, I agree, it shows that gauge theory interpretation of typical equality fits gauge theories pretty well. But that doesn't issue any sorts of conclusions about the BHK interpretation, because what's going on between gauge theory and type theory is just separate from what's going on between logic and type theory. And this is good because, pure logical mathematical thesis couldn't have any direct consequences for physics anyway, right? Really briefly, here's some sort of future direction I think that, I or some devs could pursue here. Well, if not Katren's conclusions, then what, right? I think still there's compelling reason to think that this sort of homotopic, abstract homotopy methods or whatever are illuminating in the same direction. But, if I don't like Katren, what should one do instead? More precisely, maybe, how does the homotopic conception of structure differ from the one found in the various Korean Buchert arguments that allows it to avoid them? And, is it really a notion of structure? What's structure supposed to be in the first place? Why do we care about structure? What's the relationship between structure and PII and gauge theories? And then second, I said before, maybe you could come up with some kind of story that connects mathematical representation to typal identities and gauge theories or whatever. All of the theories of mathematical representation that are sort of on the market right now pretty violently or flagrantly conflict with the sort of homotopical features that Katren's interested in. And so one needs something entirely different. What could that look like? Okay, so those are setbacks.
Excellent. Thank you very much. It is our tradition that we start with questions from the other center or maybe other people who are on Zoom. So Chicago, Sakshi, Radva, does any one of you have questions? Nick?
Well, Ray has a question. Sorry, he put his hand up slower.
I just had a quick clarifying question.
Sorry, I can't hear.
Oh, sorry. Can you hear now?
Sweet.
I think it's a volume thing on our end that maybe Niels is helping.
Yeah, I can try again.
Ooh, okay,
Can we have it somewhere in between?
I see, this should maybe be good,
Hello?
that's good.
Okay, I just had a quick clarifying question. Throughout the talk, you a few times, or mainly, I suppose, talk about distinctness of situations. How are you understanding that? Thinking that in terms of physical distinctness, in terms of like we can conduct an experiment to really separate these two situations, or yeah, I guess I just wasn't super clear on what you mean by distinct. In the sense
Okay.
of which,
Sorry, I understood, I caught the structure of this question, but not the key term in it.
distinctness is the key term.
Sorry, one more time.
Distinctness.
Distinctness. Yes, thank you. Sorry, I recently lost hearing in one of my ears and it's been throwing me off.
I think it was difficult for all of us.
Okay, good. Okay, good. Okay. Anyway, so distinctness. Yeah, so this is, I think, is a great question. I think it's a difficult one. And so sorry that this will not be a satisfying answer. But I think there's two things going on. I think that oftentimes by default, recently when people also in physics have been talking about distinctness, what they've been thinking is, look, there's some sort of fact about the ways the world could be given to us by metaphysics, right? There's just modal facts out there, maybe not fundamentally, maybe they're given to us by sort of unique recombination or something like this. But you know, there's definitely this like modal landscape. The theory is after correctly representing that modal landscape. And so when we interpret a theory, what we're trying to do is understand what the modal landscape is sort of in concert with the theory. And so what we're interested in is with distinctness, is we're saying like one thing that we might try to do to get our theory to hook up with the modal landscape in the right sort of way is to get two different things on our mathematical side to also be different on the physical side. And tacitly, I take the distinctness on the mathematical side to be presupposed to be something like, well, look, what's a gauge field? It's, you know, an assignment of a vector to every point. Two gauge fields are different if there's some point to which they assign different vectors. That's why we have distinct things representing the same physical state of affairs, because the thought is, on the mathematical side, the theory itself, if we're being careful, the theory itself says that they're different, but we, the interpreters standing outside the theory, looking at the theory and the world, we see somehow that they're the same on the world side and they're different on the physics side. I am dissatisfied with this, partially for personal prejudice reasons. Not being a realist, I think this presupposes the kind of realism that I'm not fond of. And I think that the way that normally an anti-realist does this sort of thing and thinks of it as a respectable sort of activity is to say, well, we all think the theory says something determinate. And so what we're doing when we're doing this sort of like realism game where we've got the world on the one side and the theory on the other is we're talking about a second theory. And what we're trying to do is argue or design a better version of the physicist theory. Of course, physicists give us theories that have all these bells and whistles that aren't really part of the metaphysics and aren't really part of the theory. They're just sort of computational conveniences to say. And so what we're after in this sort of interpretational game as realists, we're after what is like the real theory that actually pictures the world exactly right. And so what we're doing is we're sort of designing a new theory that is going to get the same counting right on either side. And I think this is why, when you look at the literature, especially in formal philosophy of science on these sorts of issues, counting is sort of like the main question they're interested in. How do we count possibilities? And I think this is sort of the reason why, because they're interested in something much more general, but counting is sort of an easy first pass at how many worlds are there and how many models are there of the theory. So I think what we need instead, or what I want instead, or what I'm after instead, or something like this, is something like, well, great, we can have a different kind of theory, but tell me what that theory is explicitly. Instead of treating it as an interpretation of the first theory that just gives a different story about how it relates to the world, because that's just more theory. Give me a different theory, and then I'll look at what the content of the theory is, and then whenever I'm talking to a physicist, I'll pretend I believe it, and I'll talk to them fine, and then whenever I'm in the philosophy room, I'll try to come up with, you know, do whatever my anti-realist thing is, whatever my motivations are. And I think that because of this picture, this sort of distinctness question sort of drops out. And what we get instead is something like, when pressed, an interpreter of gauge theory is going to say, oh, well, I mean the equivalence classes. I mean gauge equivalence classes. And that's going to impose sort of the distinctness stuff by fiat immediately, because we're just saying that these things are the same. And so we can just stipulate that the counting is gotten right. And that I think one can interpret as part of the theory then. And so then if the proposal is take these equivalence classes, then that's a new theory. That theory says certain things about it. That theory just says these things are the same. It doesn't say there's anything redundant. It doesn't say, that somehow is representing them as the same and as different, or you can't take them to represent distinct things. It just doesn't, it represents things in this theory, which is naturally associated with this theory, are what two things over here, they're one thing over here because they've been identified. And that's really all we're talking about, two different theories. And so, yeah, I guess the shorter version of the answer is, what I mean by distinctness, I mean different possible words.
Thank you very much.
All right, do you have another question, Chicago?
Well, I did, but that's sort of addressed. I don't know that. That goes to some of it in a way that's a bit. I'm not quite sure how to ask the question. I feel like there's residue in my question, but I don't know how to pull it out after that, because that actually is extremely sort of helpful and clarifying. Maybe ask in a different way. So the thing you sort of said at the end, the thought I had was you at the beginning, and I sort of see why in a different way now. You were pressing on, look, the theory can't sort of say these things about how to represent and so on. And yeah, of course, I agree that with that, you can't sort of start talking about what you can or can't represent until you have sort of, some sort of statement about how it is you're taking the theory to represent that is, I think in the way you're thinking about theories, sort of, if you think about theories formally, which I think is how you are thinking about them, is extraneous to the theory. One might think that the interpret theory in a broader way, right, in a non-mathematical way, but that is part of the theory. So that's part of it. You're thinking about, so when you talk about theory, you do mean in that sort of formal way. I guess the thought I sort of had was, is there a way of taking Catran as sort of saying, not, that we have to kind of interpret things this way and that gives you the can't, but look, if this is how I'm now telling you, here's my mathematics and here's how I think it should be interpreted. Then that's a weaker claim. They're not saying, this is really what you've got to do, but if you want to, it's a way, I guess this was my sort of thought, that you might sort of say, like, this is a way of just being sort of perspicuous about, what I think it's representing. I take it that's sort of probably too realist, or something, for you, but that was sort of the thought. Is that the right way of sort of thinking about it? And, yeah.
Yeah, I think so. So right. Guilty is charged with the formal way of thinking of theories. There's various sort of motivations in the background for this beyond just liking math, but I think they're not directly relevant here. This issue of sort of, interpreting Catran this way. So one thing that I didn't sort of press on as much as I think is important is that I think he's right that there's something really novel about the sort of, at least the typal equality type interpretation of the things going on with the of gauge theories. One part of what I would like to say is that however he works out the sort of first part of the argument, the qualitatively distinct but numerically identical, I think is it's being offered as, just as you were saying, like here's a perspicuous representation of the content of the theory using this sort of new language that I've got for making distinctions that I could only sort of implicitly respect before. By making sure by refraining from distinguishing between isomorphic things or whatever, now I can just say they're isomorphic but unequal or something. So I do think this is kind of the picture he has in mind, and I think the problem with it, the biggest problem with it from my point of view, is that it doesn't answer the practical side of the why can't we. So I think there's really two things going on with this talk of can or can't represent. One of the things is what you were just referring to here, which is like, well, yeah, I can't say P and not P. There's an obvious sense in which that's true. And so if I am, adopting this sort of method of making perspicuous what I mean, and then I go back on it or I contradict part of it, then there's a clear explanation of the sense in which I can't do that. And I think that is sometimes part of what people have in mind, and I think it's mainly what Katrin has in mind. I think there's a second thing that I think Balot has really been trying to push, which Katrin doesn't address, and it's just because he doesn't talk about it in the paper, in part because he sets up the problem slightly differently, which is there's sort of a practical sense in which one cannot treat gauge equivalent things as distinct, even numerically distinct, say I, and that treating gauge as just one more kind of symmetry is no good. And I think that I've tried to come at this from different directions in various papers about like, well, you get non-unitarity, and your paper, right, about anomalies and so forth. Like there's one where anomalies are really, really bad. Why are they so bad? Well, because it doesn't respect the gauge structure. Well, why do we want to respect the gauge structure? Well, because unitarity. Like that's a practical consequence that I think is important and good and can be explained on sort of my preferred understanding, or that will one day exist of this sort of homotopy paradigm. But I think on Katrin's can't be, because for Katrin, these things can be broken. And he thinks, in fact, must be in certain contexts. And that's sort of, this is getting more and more inside baseball-y about the difference between the two views. But I do think this is just a sort of, it's helpful. I now see better that there's really two sides to this can or can't business, one of which is a kind of, practical incoherence about the kinds of derivations you're doing, and the other one is this kind of logical, I've adopted this formal system, and then once I've adopted a formal system, I've adopted a set of rules for myself, etc. And I should more carefully distinguish between these. Thanks.
Okay, good. No, that's very helpful. I think the one thing I was just going to add was the other sort of can't, the sort of deontic one, is coming from sort of Ehrman's principles, right? About somehow the structure of the theory should match the symmetries, sort of, from the space-time case to the gauge kind of case. There's a sort of, something like a simplicity or, matching kind of some kind of prior principle also that's maybe people have in mind when they say the can't there too.
Yeah, good. I'll write you an email about that because I don't see it exactly, but I need to think about it some.
Okay. Thank you very much. Really nice.
Okay, it looks like there's another question in Chicago.
Hi, thank you for the talk. It was really interesting. I had a quick clarifying question, just about why I'm a little bit lost on why homotopy theory is being used sort of in the first place. The way I understand it is it's kind of like Nick's coffee cup and a donut are part of the same cohomology group. So I take it that like members of the same cohomology class are obviously not the same. That was what I was thinking, but so I'm curious why kind of how this is being used to in the argument here. I was just wondering if you could clarify a little more about that. I think it was kind of lost on me.
Yeah, absolutely. So I can try. So good. I guess two quick remarks off the top. First, as I sort of alluded to on that one slide, like, yes, historically this sort of was first developed in sort of algebraic topological context of the sort of donut coffee cup business, which is exactly an instance of being the same cohomology class. But as time has gone by, it has turned out that I don't know what that means exactly, but it's turned out that these things are much more generally applicable. And so part of what, this is one of those things that I find very interesting because you can't find a lot of mathematicians in sort of official context talking about this, but because we now have the internet, you can go hang out on Math Overflow or whatever, and you can like hang out, you can just listen to mathematicians talk about these really irresponsible stuff about it. It's a revolution in mathematics because, whatever. You know how people talk on the internet. But so like there's definitely something here, and it's supposed to be something that's much more general than these sorts of concrete cases that were the motivation originally for these notions, exactly like the one you were mentioning. And sometimes this gets pushed to this sort of it's a new foundational perspective on mathematics or so. But I think the more interesting question from the philosophical point of view, from my philosophical point of view anyway, is like, well, what is it about these contexts that's so interesting? And I think, or that could be interesting, right? Why think there's anything special about cohomology? For example, look at this donut and mug. Why not just say these are different, even though they share a property or something like this? And I think the answer to this is, to first think about different kinds of examples. Think about the development of, say, this is an irresponsible historical story because it's not true, I don't think, but think about topological spaces. Where did these come from? Oh, well, topological spaces are like a structure. It's a structure that can be shared by different sorts of sets. And so, two different, say, smooth manifolds can have the same underlying topological space. Two different metric spaces can have the same underlying topological space. Two different algebras, or so. I mean, you can see topology everywhere once you start looking for it. And what you might think that, well, what's going on here is that I've found a new sort of level of structure I can talk about, and I can talk about these two topological spaces as being sort of the same topological space. And you can do the same thing with metric spaces or measure spaces or any other kinds of spaces that you're interested in. But you can't do it there's a precise sense in which you cannot do it in the case of homotopy. By this I mean the following. It would be really interesting and it would be convenient for all the usual sort of reasons that abstraction is convenient. It would be convenient if we could have something called homotopy spaces. It would be much like topological spaces where we would have these two different metric spaces, say, but then they would have the same underlying topological space, where the topological space captures sort of all and only the stuff, the topological features, right? If we ignore the non-topological features, we end up with the same topological space. Isomorphic is, of course, what we mean. And it'd be cool to say, well, here are these two different topological spaces, the mug and the donut, or the letter A and the letter D, or something, or O, or something like this, and say, well, look, these are not topologically the same space. They've got corners, they've got little antennae, things like this, but they are the same homotopy space. And then, if in particular you're doing this kind of thing, we're like, well, what I want to get at really here is like, what are the features of the mathematics that are actually physically contentful? What if what I'm kind of trying to do is I'm looking at the sort of coordinate full representations physicists use, and I'm trying to extract from this all and only the structure that's actually making physical distinctions. Then if for some reason you were motivated to think that the homotopical stuff, the homology groups, cohomology groups, etc., if you were motivated to think that that was exactly the right level of structure, then what you would want is you would want to say, well, of course, physicists talk about smooth manifolds, say, as being embedded in Rn for some high Rn, but the embedding has nothing to do with the abstract manifold problem speaking. And so if we're thinking of the manifold as really representing spacetime, we shouldn't be really thinking of it as embedded, even though it's convenient, and that's why physicists do it sometimes. What we should do instead is we should think about the manifold as a smooth manifold, or as a Lorentzian manifold, or whatever, as having only that structure that we've that characterizes it as this kind of mathematical object. We would want the same sort of thing in the case of homotopical space. We want homotopical spaces to be the same just in case they were isomorphic. And because we've got this kind of Phrygian structure of picture where isomorphisms are something that aren't up to us, isomorphisms are structure preserving bijections. Because we have this sort of picture, what we need some kind to identify some kind of structure you could put on a set that would give it exactly the homotopy groups and nothing more, such that the donut and the mug would have the same underlying homotopy space, in the sense of there'd be a structure preserving bijection between them that preserves all and only the homotopy groups and their consequences. And it's an interesting theorem that that's not possible. And so this thing that you would want can't happen. And so what do you do instead? Well, you develop abstract homotopy theory for these other, for dealing with this case in particular, and then you realize that these methods can be applied sort of everywhere once you start looking. And that's the sort of historical motivation for sort of the development of this abstract homotopy theory. And it's the reason that you might think that homotopy stuff in particular might be relevant for physics, insofar as you sort of, as inchoate in the back of your mind, picture of mathematical application representation being a matter of the world being isomorphic to your model or some part of it. You would want homotopy theory isomorphisms. Those don't exist, at least in the sense that we are usually assuming in these stories. And so that's why you might think homotopy has something, there's something special to say about that case. So does that address any of your question at all?
Yes,
Awesome.
thank you.
All right, great. Thank you very much. Lorenzo.
Yeah, thanks for the talk. I really enjoyed it, although I don't think I understood most of it. I would be honest that I Googled the paper you're responding to yesterday when I saw the email, and there is an alarm that rings in my bell and says crackpot, crackpot, crackpot. It brought me back to the good old days when I was a median working on the Beyond Space-Time Essay Prize.
Oh, sure.
And I wanted to ask you if I understood correctly what the argument was at the beginning, especially in the first part, or if I am strawmanning because of my prejudice against the French or something. So the idea was,
I think it's half French. I don't know. I think, yeah, but I could be wrong.
well, I just, maybe it's Belgian.
We're live on YouTube, by the way, right?
I don't.
Okay.
Step one is in mathematics, allegedly, standard mathematics presupposes or follows the PII. Step two, but there are physical reasons. Mal Guterres showed that in physics we don't want the PII.
Okay. Should I interrupt you or should I let you finish?
Well, it's already wrong. Interrupt.
Oh, yeah. So the first step, it's not the standard mathematics follows the PII. It's that standard mathematics flagrantly violates the PII to such a degree that it's bizarre that philosophers try to save it ever.
Standard mathematics violates the PII.
Yeah.
Okay, and then so what was the point then of the physics example with the
To show that the PII has to be violated, despite, so neighbors address the philosopher saying you philosophers always try to save the PII in your reconstruction of physical theories. Don't do that.
Okay, then what's the point of them using the homotopy type theory vis-a-vis the PII? It doesn't save the PII, so what does it do?
He doesn't think it saves the PII. I think that whether or not it saves the PII is orthogonal to the argument of egos.
I thought it was supposed to get rid of the PII from mathematics.
Yeah, sorry. Sorry, I'm getting confused on my view. Yes, his view is mathematics never had it. Philosophers are confused about this. How can philosophers understand what's going on in mathematics in a way that sort of satisfies their intuitions about the PII and what mathematicians actually use? Answer, mathematicians use two different sorts of equivalence relations. There's numerical identity and there's isomorphism. And philosophers constantly, especially philosopher physicists, constantly try to collapse these two together by taking equivalence sizes of things. But they should not. They should just live with the fact that they're numerically distinct but isomorphic things.
What?
Which part don't you like?
I don't think you need to.
Yeah,
Just stop doing that. Stop doing that.
Yeah, people on YouTube have motions.
Yeah.
This.
This joke.
Okay. Yeah.
So it's a device to explain to philosophers how the PII is violating mathematics.
Rather, it's a device for allowing the philosopher to keep their metaphysical scruples while also admitting that the PII is violated in mathematics.
To reconcile the intuition of the philosophers with the violation of the PII.
Yeah.
All right. Now, I'm not sure exactly what the intuition of the philosopher is supposed to be, but what I took your point was, well, if you want just to have a consistent mathematics or anything without the PII, you clearly don't need to have homotopy type theory. It's like having like a thermonuclear weapon to apply or something. There's just the predicate logic, there is nothing there but the PII. Is that your point about framing?
Yeah,
Okay,
sure.
okay.
There's
a great point.
There's a slightly further point, but that you won't like, which is that I have no particular love or hatred for the PII, which is unfortunate because it would make the argumentative dialectic much easier if it did. But he finds his intuition underwritten by the way that sometimes mathematicians will talk about numerically distinct but indistinguishable sorts of things. I think that only gets underwritten by adopting sort of Freudian picture, because that forces you to have all of these indistinguishable things. It forces you to introduce this kind of numerical distinguish that doesn't do anything for you. But this is a slightly different argument.
Okay, maybe the last thing, let me just apologize to the Gabriel guy. I called him French and he's Belgian. I didn't want to do that.
I have a question. Sort of abstracting away from the particular points against Catherine, I'm interested to think a little bit more about structure. So the point of the argument I gave anyway against people who are ontic structural realists of a certain kind with respect to physical structures, and they want to keep the PII, then they have a problem, because that seems to be a set of commitments which is not consistent with the way physicists think about their models and the mathematics they use to describe that. So something has to give.
Yeah.
And of course, one thing you could reply is you give up the PII. But that seems to be somewhat unsatisfactory as long as you all don't, at the same time, think a little bit more deeply about what it is to be a structure and the conception of a structure you should adopt.
Mm-hmm.
And I think that here's a chance for us to do that using homotopy theory, the conception of structure, which will avoid the sort of troubles we got ourselves into, the morass even perhaps there. Yet I don't quite understand what that conception is and how it avoids the morass.
Yeah.
And I would be extremely grateful to you if you could roughly say what's going on and what that conception is.
Yeah, no, I would love to know too. I think I'll say a couple of things. The specific so yeah, first, as you said, there's a number of things going into this argument. Here it was being reconstructed as an issue of PII, and of course, in your paper and more generally, it's really sort of you can't hold a number of things simultaneously. The kind of attitude that I think one is motivated to take from reflection on the homotopy stuff is to give up that notion of structure. And so, maybe the PII is false too, I don't know, but that's not, I think, what one should learn from that particular argument. But just saying, oh, I don't like that theory of structure doesn't mean it's not satisfying, it's just denying working premises, which you're always welcome to do. I think having a positive view is something that I would love to know more about. So there are various people who have pointed the way, so or have said things about this. So Steve Audi is somebody who has a paper about structuralism in homotopy theory. I think it's called Structuralism, Invariance, and Univalence. I think that's the title of it. David Corfield is also made some moves in this sort of direction. But I think a satisfying answer to this question needs to also be clear about what exactly structure is supposed to be doing in this kind of argument. So certainly, I think Audi and Corfield are clear. They're interested in structure as it appears in the philosophical program of structuralism within mathematics, which good. That's a particular sort of thing to be interested in. For the kinds of cases that you're looking at, or that I'm looking at in that paper, that's not going to be quite enough. And it's at least not clear to me that we're going to be able to port it directly over from the mathematics to the physical case by treating physics as mathematics. I mean, in fact, I generally don't think that's not something that one could do. But unfortunately, so far I've only been able to come up with various way of denial things. Well, it's not this, it's not that. And I think it's sort of hard to say. I mean, well, it's probably it's sort of recording makes me hesitant to do this, but I mean, I think that really what's going on is that there's really something like the kind of transition or difference between Phrygian logic and what came before, that there are certain kinds of things that can be articulated in Phrygian logic that couldn't be in categorical logic. Things about multiple quantification, things about the relationship between disjunction propositions, things about reflexivity, etc. That adopting a functional, that is to say, thinking of the proposition as a function of its constituents, it's an innovation. It allows you to say new things and allows you to have this new picture of structure whereby you've got a set equipped with subsets, and those subsets are extensions of various predicates and things like this. And so sets on sets and sets, and then you have this notion of isomorphism that sort of comes along for the ride and structures whatever is preserved by isomorphism. But in this sort of conception, that's because of the definition of isomorphism. And so isomorphism preserves structure because we have a pre-theoretic or a prior notion of structure, which is sets and subsets associated with the signature. I think the thing that is novel or interesting about homotopy theory is the thing that comes out a bit in that passage from Real I quoted, which is in these cases, we're stipulating what the isomorphisms are and then working backwards. Now, of course, our stipulation of what the isomorphisms are is such that they end up being and behaving like isomorphisms in the old algebraic structure preserving sense. But there's no reason for them to be structure preserving in that other way, in part because we're allowed to stipulate, right? And when we stipulate, of course, we have to respect certain features of isomorphism, just like when Frege wants to stipulate equalities, there's certain features of identity that he has to keep himself obey. But because he had introduced this new language for talking about what those requirements are, he was able to meet it. And I think that homotopy theory is a similar sort of, it's able to articulate these sorts of features of isomorphism that it then wants to be able to respect when it stipulates what the new sorts of notions of isomorphism are, from which one works backwards to a notion of structure. But this is very dissatisfying in part because it doesn't tell you what structure is. It's defined structure as whatever it is that's preserved by these maps, or these maps are the things I've just picked out because I care about them.
Yeah, it seems somewhat empty as a concept of structure.
Agreed, yeah. And nevertheless, it seems like it's just a different direction of the duality that we had before, where isomorphism is an empty concept because it's just determined by whatever the structures were. And before that, identity was an empty concept because A equals A, and that's the end of it. Now, it's not like we have really resolved it, but I think there's similar sorts of problems. So, yeah, sorry, I don't have an answer, but these are my thoughts on it. I mean, I think really for me, what would be coolest, the thing that I would love the most right now is just, there's these stock examples of what Frege could do that Boole couldn't. There's like 3 that everybody uses in the literature. I would love similar ones. What can functorial dependence do that functional dependence cannot? And I make this an exercise when I teach category theory, and nobody's answered that exercise yet, but maybe one day, maybe this term.
Yeah. Great, thank you very much. I think Nick has a question.
I know you don't really want to talk about PII too much, but and in fact, this is a question, something you sort of said about trend, just that I didn't understand. Didn't understand, which was about the FLRW universe and how this is a count. I don't. What are they? What does that? I mean, the points are definitely weakly discernible. I don't kind of get why. So, right? I mean, the relation in mind is, there exists an open set that contains X and not Y. So it seems like, it's irreflexive and symmetric. Yep. So they are weakly discernible. So what's the claim exactly that's being made?
I've not been able to pin it down to my satisfaction. The claim, as I understand it, is something like, it's a, I can't remember the name for this sort of argumentative strategy, but it's something like, sure, of course, in this case, you're able to come up with a device that does that. But look at this other case where it needs a different device, and this other case where it needs a different device. And shouldn't you just think that this is a bunch of sort of ad hoc stuff in each case for saving a particular kind of discernibility that gets ever weaker? And shouldn't you just reflect on, well, why do you want discern like PI in the first place? Why should we? Yeah, and I think
my comment wasn't coming from a place of wanting it. I guess I'm kind of neutral at the issue, right? But it just seemed kind of false. That's a counter.
I mean, I've had prominent structuralists reply to me in print along similar lines, I take it. And I think one problem with the strategy is that it sort of seems to beg the question, at least to my mind, because you sort of presuppose that there are, some relevant relations at hand of which you already know somehow independently whether they're reflexive or irreflexive or something like that. And that seems to then say, and if you say that these relations are instantiated, in fact, in the structure at hand, you already make a decision about whether there's a plurality of objects there or not, which is fine. Maybe this is what you have to do. But it doesn't really address the original problem. Anyway, that's what I wanted to say in response to this. I don't know whether that helps.
Yeah. So am I right in thinking that the reply is something of that this reply is something like, yeah, case by case you can save it, but I have no general reason to think that it's always going to be saved. No, it's not even that. It's rather a sort of priority.
So the reason is, the point is just, look, I gave you an argument that somewhere, if you want to be a structuralist and keep that way of thinking about the structure and the PII, and claim that, in physically relevant cases, like in Minkowski space-time or W, we have a sort of plurality of space-time events or points in these structures, then you will also have to sort of take on board in some form or other an assumption that there is some sort of plurality of these objects around, either by saying there is an irreflexive relationship which is instantiated, or by just saying it flat-footedly or in some other way which may be more indirect. In some way or other, you have to do that, because unless you do that, I don't see how you get to the plurality.
Yeah, I mean, I think there's a kind of structure. There's a kind of structuralist where what they mean is there is at least weak discernibility that I think like Simon Saunders, for instance, I think that's kind of what he has in mind, that if you get that far, you're a structuralist, and that's all there is. So, and that's all kind of fine.
Yeah,
I see, but there might be other people who really want to not even say that. I wasn't quite. Yeah. Okay. That's good. Okay. But that's cool. Yeah.
I mean, fair enough. If you say that, then I think you've solved the problem. We're sort of out of time. Any last questions? Urgent remarks? If not, please join in thanking John once again. Please.
That's it.
Goodbye, everyone on YouTube.
Bye.
That's the final event. Oh no, you are doing one more thing tomorrow, right? For the cosmology
Yes.
beyond space time. This is not quite the end.